InfluxDB is an open source time series metrics and analytics database. Paul Dix is the CEO of InfluxDB. Paul, welcome to Software Engineering Daily.
Thanks for having me.
What is InfluxDB?
InfluxDB is an open source distributed time series database. Now, time series has a few different use cases that we focus on. DevOps metrics is one obvious use case, but others are real-time analytics. Another big one for us is sensor data. But essentially, when we think of time series, we really think of data where the primary questions you're going to ask about it is questions over time. So time is always like a primary index.
What differentiates InfluxDB from other databases on the market?
So we're solely focused on time series. We're not trying to be a general purpose database. So there are things that we do that other databases don't do for you automatically. So in the query language, you can do things like compute aggregates on these time series. And if you look at other distributed databases like Cassandra or React, if you want to compute those things, you have to write application level code to get those answers. You also have to write application level code to figure out how to distribute the data within your cluster. So we do that automatically. And then some of the other pieces are, we have a feature called continuous queries, which does automatic aggregation and downsampling of the data that you put in. Normally, this is a feature like you would have to write it yourself in your application level code to do this. And we also have something called retention policies, which has the database automatically manage the life cycle of your data. With time series data, it's very common to have much more data than you can keep indexed on a regular basis. So you end up dropping the old data and aging it out. And we manage this process for you.
InfluxDB's mission statement has changed as the product has evolved. You started out as a time series database, and then you went to the time series metrics and analytics, verticals. Why has it vacillated back and forth, and why have you settled back on time series?
Honestly, that's just a matter of positioning and messaging. The goal of it has been the same actually since we started it, which was essentially time series. The big problem we've had is that a lot of people don't know what we're talking about when we say time series database. So if we say it's for metrics, or it's for events, or it's for analytics, people know what those mean.
Fascinating. Okay, so as you said, InfluxDB is a time series database. How is this different from a conventional database where a timestamp is placed on every entry?
So part of it is in the way we index it. Part of it is in how we store things. So our data model is different than, say, like a SQL database where you just have a table and you would order by time. One, in the time series use case, it's very common to collect billions of data points a day, or even in a low, a smaller environment, you would still easily collect, 100 million data points a day. So the problem is, like, if you're growing a table at that rate, you generally have to write a bunch of application level code to like shard out your data in multiple tables and then join that together. So again, that's something that we kind of manage that process for you automatically. And the other big thing is our data model isn't strictly like tables and, columns and all this other stuff. With our data model, you have an idea of a measurement, which is just the name of the thing that you're measuring. And you can have 10 of those, you can have 100, you can have 10,000 of them. Whereas in a SQL database, you generally wouldn't have 10,000 tables. And then within a measurement, you have a bunch of separate time series, and those are defined by, a set of tags that describe an individual data point. Tags are key-value pairs, and they're like metadata that describe the data point, right? If it's DevOps data, it could be the region the measurement came from, the host it came from. If it's sensor data, it could be the building ID or the sensor ID that it came from. And then you have the actual like values themselves, which are always a timestamp and some set of values. So with our data model, the thing that we provide out of the box that you wouldn't get in a regular database is it's actually like two databases in one. So the first is the raw time series database for the time series storage, but then the other is essentially an inverted index that we keep in memory based on the measurements and tags that you have, so that we can quickly answer questions around like, what measurements do I have? Or what measurements am I taking in this region? Or what measurements do I have for this host? What host do I have? And then actually querying all those time series based on the different measurements and tags.
So you've mentioned the data model of InfluxDB. Data models are usually described as relational, key value, or document. How do these paradigms contrast with, well, I've heard you in a talk refer to the data model of InfluxDB as the event data model. So how does event data model contrast with relational, key value, or document?
Well, let's see. That's a difficult one.
Maybe it's a superset of one of them, or
yeah. I mean, on some level, like you could look at it as at a very low level, it looks kind of like a key value thing. So an individual data point is described by its measurement, its tag set, and the timestamp. So all of those things together represent the key for an individual data point. And then the value is just, the fields plus their values. So in that sense, it's a key value model. But the difference is with time series data, you often have to take dozens, thousands, hundreds of thousands, or millions of these key value pairs and combine them up and aggregate them in a way that you can send summarizations back to the user. So a regular key value store isn't really designed to do that, right? When you put time series data into a key value store like React, you have to write a bunch of logic to make that work. A document store, it's not very much like a document store, just because you generally have like the key plus this big blob, or you have this big blob of the document data. I mean, almost on some level, like the value looks kind of like a row in a relational database, because you have fields and their values, which is like columns and their values. But yeah, I'd say it's quite a bit different data model than any of those.
Sure. Okay. So to zoom out, I want to talk a little more about a higher level set of use cases. You mentioned DevOps already. I imagine that data scientists are also using time series databases such as InfluxDB quite regularly. So maybe you could give a couple baseline common use cases, different use cases for InfluxDB.
Yeah, so DevOps, like I said, metrics on what's going on in your servers, in your applications, real-time analytics, both business analytics or user analytics, essentially things where you're writing this data in and you're doing aggregations on it all in real time, where real time is in the hundreds of milliseconds or less kind of range, not in the like microsecond range. And let's see, I mentioned sensor data before. The thing about sensor data is the structure of it looks very much like DevOps data. The only difference is you're taking measurements from physical sensors, as opposed to DevOps. All of your sensors are software. They exist in your servers or your applications. And then the data science use cases primarily revolve around those things. Like, are we taking event data from users and doing data science on that? Are we taking sensor data and doing data science on it? And then I guess the last use case would be, in financial market data, but it's not something we're really targeting. Like, we know people are already using Influx in financial services, but it's not a focus of ours at this point, because there are already other players in that space that are serving them pretty well.
What would be the the hurdle that you would have to overcome if you wanted to target the financial space as well?
Well, one, there are a couple of well-known competitors in the space. A company that puts out a product called OneTick, and another company called KX Systems that puts out KDB. And if you talk to the users of those systems, they're generally happy. Those are very specific. They're designed to store tick data from financial services, so they're very, very specific. Whereas we're a bit more general purpose than that, even though we're focused on time series. But generally, what I found in financial services is they have a much lower tolerance for newer software, for open source software, and particularly for software that's still early stage.
To dive a little deeper into the internals of how a user works with InfluxDB, what is the API for inserting to the database?
So we have a number of different input plugins. You can insert data through HTTP, and you just do a post to one endpoint. You specify what database you're writing into, what retention policy, and then we have basically like a text-based line protocol where you specify one data point per line. And what it looks like is you have a measurement plus a set of tags plus the field values, and values can be either booleans, integers, floats, or strings. And then you have a timestamp, which is a nanosecond precision epoch. And so HTTP is one way. You can also send the line protocol over UDP. We have an input plugin for OpenTSDB style data. So if you have an OpenTSDB library, you can just point it at InfluxDB and write that. We also accept the Graphite protocol. That one's a little bit trickier because Graphite's data model doesn't map cleanly to what InfluxDB's data model is, right? In Graphite, you have these long strings that are your metric name, whereas we push users to split things up using measurements and tags so that it's more efficient to do discovery and queries later on.
What about the API for querying the database?
That's just an HTTP GET. There's one endpoint. We really are not focused on HTTP is just a transport for us. It's not RESTful or anything like that. What we wanted to do was expose a query language that we could iterate on and improve, where people could write client libraries in any language. And then if we had a release where we added new functionality, they wouldn't have to update the client library in any way because the whole thing's just exposed through a query language. So anything you can do in the database other than writing data can be done via the query language. And it looks kind of like SQL, but it's a bit different than SQL. We kind of made it different so that we thought it would be a bit more expressive and easier to do queries where you're saying like, give me the 90th percentile of this series for the last 4 hours in 2-minute increments.
How are you seeing InfluxDB fit into the full stack architecture? Are you seeing people build around InfluxDB specifically, or are you seeing people augment their current architecture with InfluxDB?
We've seen both, actually. I mean, it depends on the stage of a project. Obviously, like new projects are the only ones that are specifically building around InfluxDB. And what we find with that is the people who are doing that are people who are building an application where it has some sort of analytics component in it, like some sort of dashboard or something like that. And then they can build that particular feature around InfluxDB. But generally, for the usage that we've seen, it's always people who are doing polyglot persistence, right? InfluxDB isn't designed to be the only database you run. It's designed to be one of a number of databases you run. And you'd run like either Mongo or a SQL database in conjunction with it to store all of your metadata around other things.
So I've already talked to people from RethinkDB and MemSQL this week, and both of them said that polyglot persistence seems to be an empirical reality, but is not necessarily, ideologically at least, it doesn't seem to be the optimal way to do things. But they're very hesitant to say, oh yeah, we should have, theoretically, we should have some sort of one-size-fits-all database, but there seems to be this this friction between the cognizance that we need polyglot persistence and the frictions and maybe technical debt that results from polyglot persistence. So, what do you see as the future of polyglot persistence? Do you see any sort of consolidation, or do you just see further fragmentation?
I mean, if there's any consolidation, it'll be around like use cases, but I don't for complex applications. I don't see a situation where a single database works, right? It's the old saying, no silver bullet, right? It depends on your use case, and there's a large swath of applications for which a relational database is all you need. But for many, many things, a relational database is what you need for one part of the system, but for other parts, it won't work and it will fall over. And even if you had a magical relational database that was horizontally scalable that would go to forever, there are still other reasons to use a different data store, right? You get better compression or better throughput, or more features out of the box, so you have to write less application code. So realistically, I don't see polyglot persistence going away. I see more and more people adopting polyglot persistence and getting comfortable with the fact that there isn't one database to rule them all.
How do you weigh the trade-offs of adding a new database to your architecture?
I guess, well, I've never been in a DevOps role, so I assume that DevOps people are generally much more gun-shy about adding new services to their architecture, whereas developers are, which is the role I've always been in, I'm just optimizing for how do I ship features to my users as quickly as possible. And if I find a data store that will do that, then that's what I'm going to use. So for me, I guess in previous environments, I would typically run, it wasn't uncommon for me to run 3 data stores. I would run a SQL database like Postgres or MySQL. I'd run Cassandra for the horizontal scaling piece that I needed, and I'd run Redis for the high speed, in-memory index stuff.
Do you think that augmenting your architecture with a new database maybe has less potential technical debt than augmenting it with some sort of new service, like that you're actually writing yourself, or like a new framework? Because a database inherently has some sort of model that's it gives you a little more tighter notion of the API or the spec. Therefore, it's easier to if it becomes technical debt, it becomes easier to excise that database and rewrite your architecture around other database solutions.
I mean, I don't know that a database gives you that any more than, say, a well-defined service layer does. If you write a service and you find that it's just not doing very well, it's not performing for whatever reason, you can rewrite the whole thing if you want. I think really where the technical debt comes in is any code you write yourself is code that you'll have to maintain. So if there's a popular database that's actually going to make it so that you have to write far less code, and it actually has good velocity around it, and it gets continuous improvement, then that's less debt you're going to have to take on yourself. But at the same time, there are services that open source services that are well written that people maintain that it's the same thing. That you would pick that up, and then you don't you get the advantage of letting other people in a community around an open source project push it forward and help maintain it.
Right. You give a talk at the dotScale conference called, quote, "TimeSeries Data, the worst and best use case in distributed databases," end quote. And I'll include this in the show notes. What is the message that you were trying to get across in that talk?
Mainly that time series data has different properties to it than what you would than a normal database. There's some key properties around time series data that make them kind of a degenerate use case for a regular database. One is high write throughput, but actually, often you have just as high or even higher read throughput. A lot of people think with time series data, you end up writing a lot of more data than you read. But if you have monitoring systems and real-time dashboards that are continuously hitting your database, you end up reading your data far more than you end up writing it, which is, again, all of this is like high throughput, right? Distributed databases, it's really, high throughput is a pain in the ass. And then one of the other things that I mentioned in the talk was deleting data, right? So with time series data, it's very common to collect a lot of data, more than you'd want to keep indexed for all time. So you have to come up with a scheme where you have high precision data that you keep around for, say, 7 days or whatever, and you downsample and aggregate from that, and then evict the high precision data as it ages out. Now, what that means functionally is once you reach your time envelope, call it 7 days, if you were to do a 1-for-1 deletion of a record going in to a record going out, you'd be deleting just as many records as you're inserting. Most databases aren't designed to do that. The assumption with most databases is that you're keeping your data around for all time, except for like the occasions when you do delete it, but deletes are few and far between compared to inserts or updates.
And you mentioned that high read throughput, in addition to the high write throughput. Does that high read throughput tend to come from continuous querying?
It comes from the real-time dashboards, and it comes from monitoring systems that people build. Monitoring systems can be alleviated by having a data pipeline where you pump all your data through a queue, and you have listeners pull off the queue and write to the database, and other listeners pull off the queue and do the monitoring. But if you want to build more complex monitoring that isn't just reliant on the stream of data that you can see that's recent, like say you want to take historical data into account, you end up having to query the database for it. So that hits it. And then of course all the real-time dashboards that people have up on their monitors, that's just querying the data as it comes in again and again and again.
What are the cap trade-offs that InfluxDB makes?
So we are it's kind of a two-stage system. It's actually two different distributed systems in one. So it's almost as if you would have one system that's CP, which is the system that stores information about what servers are in the cluster, what databases exist, what users, what continuous queries exist, and also what shards exist and where they are. Shards in InfluxDB are a unit of data, which are generally anywhere from 1 day's worth of data to 7 days worth of data, not for the entire day, not for the entire set. We split a day's data across many shards in a cluster. But that system is very low throughput because we only have to update it, when new shards get created. So call it once a day, we'll have to update it, or when a new server joins the cluster, or when a server leaves the cluster. So that's designed to be a CP system. The rest of the system around queries and around the write path, is designed to be an AP system. So it's eventually consistent. And our goal there is to optimize for throughput and the ability to actually take a write.
You mentioned sharding. I think that dovetails nicely with a discussion about data locality. How is data locality important to building a distributed database?
So that was one of the reasons we chose. That was one of the reasons, like initially when I was looking at InfluxDB, that I wanted to build it as an entire database itself, because I built, quote unquote, time series APIs on top of other distributed databases like Cassandra. And the problem is, if you want to do something like compute, a count or a min or a max on a set of time series data, what you end up doing is you hit the database, you query all of the data, pull it over the network, and then you do your computation and you send the summary tick back to the user. So with Influx, we wanted to own the entire stack so that we could get data locality. Data locality is the idea that, Hadoop, or that Google's MapReduce first pioneered and then became popular in open source in Hadoop, which is you ship the code to where the data lives, not the other way around. So within InfluxDB, we have a MapReduce framework that we've built that's custom built for the time series use case, and all of the queries that you can do in Influx can be decomposed as both a map phase and a reduce phase. So the map phase is what runs locally on the machine, so you can churn through as much data as possible and send only the summary ticks back to the machine that initially issued the query, which will then do the reduce phase and then send the final result back to the user.
InfluxDB was not initially a distributed database. Could you describe the process of building out the distributed functionality?
Well, so I guess technically we're still working on the distributed parts right now. The next release on Friday will start lifting some of the limitations around how many servers you can have in a cluster. And then the following two releases in September will add more functionality around the distributed piece. But we knew from the very beginning that we wanted it to be a distributed database. And we went through, over the course of 2 years, probably about 3 or 4 different designs for how the clustering system would work. Which was very interesting to go through all those different pieces.
Is interesting a euphemism for difficult?
Yes, yeah. Building distributed systems is extremely painful and hard. But yeah, we've landed on a design that I think is more robust now and has potential for much greater scale than some other approaches we were taking previously. So I'm pretty happy with where we are.
You use Raft to maintain consensus among your replicants. How does Raft differ from Paxos?
So I'm not intimately familiar with Paxos, so I'm probably not the best person to answer this question. I read the Raft paper, and Raft was designed as a consensus algorithm that was hopefully easier to understand. But yeah, beyond
that's not saying much compared to Paxos.
It's not a very high bar. But to be honest, I haven't read the Paxos papers yet, so I can't really give an educated answer on how the two differ.
So why did you choose to use a Raft implementation written in Go rather than use a service solution like Zookeeper?
Ease of install and ease of management. One of the things, again, one of the other motivators for us for developing the entire distributed database from scratch rather than writing web services on top of some other distributed database was we wanted to be easy to set up, and we wanted to make it so that people didn't have different moving parts to manage. We certainly, as a project, Influx would be much farther along if we had just built on top of, say, HBase or Cassandra. But ultimately, the user experience of getting it set up and then later managing it, we thought would be better if we just decided to do the hard work and build all these pieces ourselves. And honestly, for Raft, we didn't actually build our Raft implementation. Under the covers, we're using the Raft implementation that HashiCorp wrote for console.
What is LevelDB?
Okay. LevelDB is an open source project that was written at Google, primarily, I think, initially by Jeff Dean and Sanjay Gemawat, to do storage. I think it was initially for Chrome, but it is a log structured merge tree, which is the same kind of data store or storage engine that Cassandra uses under the hood.
Could you define more generally what a log structured merge tree is?
Sure. The data model for LevelDB it's a key value store where the key space is ordered. So what that means is you can do very efficient range scans through the key space, which is useful for time series data because time series is all about doing ranges of time. So how LevelDB works, how log structured merge trees work, is you essentially write all your data to a log. Writing data to logs is super efficient because it just appends. And then it has things called mem tables and SS tables. Mem tables are in the indexes for the key space that it keeps in memory, and SS tables are the immutable indexed files that it writes out to disk. And then what it will do periodically is it will do what's called a compaction, where it will take some of these immutable files along with the mem tables that are ready to be compacted and merge them all together into a larger SS table file that can be read from efficiently.
Right, and just to put an emphasis on that, I think I heard you say that LevelDB's key ordering is very helpful for InfluxDB's implementation because you can order the keys by the time series, and the time series is sort of the first principle of InfluxDB.
That's right. Yeah, the fact that the key space is ordered means that you can do efficient range scans. So we had time as a primary component of the key, which means we could scan through specific blocks of time very quickly. VoltDB, the memory map B+ tree, also has the same model. It's a key value store. Yeah, it's a key value store where the key space is ordered, so you can do very efficient range scans on the key space.
In the dotScale conference talk, you discussed needing a brand new storage engine at InfluxDB. Can you talk about the context of needing a brand new storage engine and then the requirements for that storage engine?
Yeah, so the two primary types of storage engines we looked at, I mean, I guess there are three. When people think of time series data, the most common thing they think of is what's called a round robin storage engine, which is what RRD and Graphite use. The problem is those assume that you have regular time series, which is you have samples at fixed intervals of time, like once every 10 seconds or once a minute. And when you have a new series, you pre-allocate your length of time. But we needed Influx to be useful for event-driven data, which is irregular. You don't know when it's coming in. And we didn't want people to have to define those things ahead of time. So round robin was out. The first thing we looked at was LSM trees. So LevelDB is well known for this. Cassandra is backed by an LSM tree. React has LevelDB as a storage option. LSM trees are optimized for write throughput, and they're really good for this. They're optimized for write throughput in a random for basically what are random inserts in a key space. And they still do pretty well for read throughput. The nice thing about LevelDB is you get compression out of the box for free. That's really nice. But one of the things I mentioned before was we have a need to do efficient data eviction. Now, deleting a single record in an LSM tree is actually more expensive than a write, because what you end up doing is you write a tombstone record and then you do a compaction later on to clear up that record. And the thing is, before you do the compaction, all those tombstone records actually slow down your query performance because you have to merge the live records with the tombstones on the fly to see what's your valid data set. So basically, if you want to do efficient data eviction, and this is for the time series use case, this is what people do typically is, like, if you're storing time series data in a SQL database, you'll store blocks of time in a table. Because in a SQL database, a table maps to a file, and it's very efficient to just drop a table because you're just deleting a file. You're not updating any indexes or anything like that. So in using LevelDB, the idea was we would create a separate LevelDB database per range of time that we're working with. Now, the problem is LevelDB stores all of its data in all these little files. So if you have lots of LevelDB databases in a process, you end up having way too many open file handles. And by far the largest source of bug reports in older versions of InfluxDB were people having problems with the number of open file handles on their system. So we said, okay, if we can't use LevelDB because we can't efficiently evict data, and there were a couple of other desires that we had, which was LevelDBs in C++, So using it in Go, it makes our tool chain to build the binary a lot more difficult. We wanted something that was pure Go. And then the other thing is LevelDB itself doesn't have the ability to back up a database that's actually open. You can't do hot backups. Now, HyperLevelDB and RocksDB, which are forks of LevelDB, fixed this. But again, they still have those other problems that I was talking about. So the next thing we looked at were memory map B plus trees. One famous one is LMDB, and in Go there was a port of LMDB written by Ben Johnson, who works with us on InfluxDB. And memory map B plus trees have a few nice properties. Well, one, in Go, it's nice because Ben wrote that pure Go version of it, so it simplified our tool chain a lot, and it makes it easier to build for other architectures and operating systems. But a single BoltDB is the project we use, what it's called. A single BoltDB database is a single file, so we can have hundreds of these open, and it isn't a big deal. Another nice thing is with a memory map B plus tree, the operating system handles caching for you. So we don't have to worry about caching at all. We just let the operating system use its caching to know what data set is hot. But the issue with a memory map B plus tree is that it has really slow performance for writes if you're doing random inserts in a key space, which we are, because we're inserting in many different series all at the same time. But the read performance is really good. So what we've done in the release that's coming out this Friday, we've essentially created what is like a single level log structured merge tree in front of BoltDB, so that all the data goes into the LSM tree first. It's basically a write-ahead log. And then occasionally it will do a big flush to the BoltDB all at once. And then we've actually built compression on top of the BoltDB install as well. So that's one of the other advantages of LSM trees over memory map B plus tree is LSM trees give you compression out of the box. We actually had to write compression on top of it, which, like I said, for the next release, we'll have. So time will tell whether or not we actually have to replace Bolt with something that's even more specific to our use case. But we're getting pretty good performance, at least in terms of write throughput, out of it right now.
What is the transaction model for InfluxDB? Like, if I update the database with a post request, what happens from top to bottom?
This depends on whether or not you're running in a cluster. If you are running in a cluster, it looks at the series key. The series key is the measurement name plus the tag set for each of the points in the post, and it figures out where in the cluster those need to go. And then it writes the data simultaneously to all of those, including if you have like a replication factor of 2 or 3 or 4 or whatever, it will try to write to the replicas at the same time. Now, when you do a write, you can specify the level, the quorum level, just like you can in Cassandra. So the levels are any, one, quorum, or all. So basically what it does is it does the write, those servers get it, they commit it to disk in the write-ahead log, and then they send a response back to the server that asked for the write that says success. Once the minimum level of quorum has been reached based on the request for all of those points, it sends a success back to the client. The important thing to know is that in Influx, if you're writing multiple data points within a request, it's possible to have a partially successful write. Now, the way you get around this, the way we get around it is if a partially successful write happens, we return an error back to you. And then what you should do is repost the data as a client. Now, for the data that you're writing in, if you specify the exact timestamp of the data point, if the clients always specify their timestamps, write operations are idempotent. So that means you can write it multiple times, and we're not going to have duplicate data points or anything like that. So that's why we felt it was okay to have the possibility of a partial write, so that, because as long as we return an error back to the client so that they can repost it.
Describe the security model of InfluxDB.
It's pretty basic. So you have, within InfluxDB, you have a concept of databases, and essentially you have users within the system. You don't have to have authentication turned on. By default, it's turned off, but you can then turn it on and create users. So there are two levels of user, basically. There's a cluster administrator who is able to do everything cluster admins can do, like create users and create databases and add servers to the cluster. And then there are users. And users have either read permissions or write permissions or both to a specific database. And that's about it.
Under what conditions can an InfluxDB read see stale data?
This is obviously only applicable to a cluster, because in a single server, that's not possible.
Absolutely.
Right. So within a cluster, one, you'd have to have a replication factor greater than 1 on your retention policy. So right now, we don't give tunable levels of consistency for queries. Essentially, when a query comes in, we examine the query to find out what servers we have to hit to answer it. And actually, we look at what blocks of time we have to hit, and then we see what servers have those blocks of time, and then we distribute it based on that. So say you have a replication factor of 3, that means for each block of time, at least 3 servers will have it. And like I said, actually, we split blocks of time even further than that in a larger cluster. So for a single block of time, we may end up having to hit 3 different groups of servers or whatever. But within a group, so a group is the replication group, we'll just hit a random one of those servers right now and read that data. So what that means is, if it's fallen behind on replication, it could see stale data. Essentially, the cases in which you would see stale data is really just if a server fell behind on replication. We have a number of things that help ensure that replication lag is as little as possible. We do the writes in real time. So when you send a write in, we try to write to those servers right away in real time. But say a server goes down, or there's a garbage collection pause or something like that, and it can't reach out to it, we have what's called hinted handoff, this is also in React, it's in Cassandra, which is basically a durable queue that we write to locally, and we just continually try to retry replicating that data. So usually that means the window of eventual consistency is very small, in the hundreds of milliseconds or seconds. And then finally, another feature that we haven't implemented yet, that will be in a future release, is anti-entropy. But that's really for solving consistency problems for a really long outage. It would have to be a multi-hour outage where servers had to start throwing data on the floor because they couldn't replicate it out to the other server.
Sure.
Now, later releases, we're talking about, it's kind of an open question at this point. One thing we're talking about is giving tunable consistency levels. The problem is we lose data locality if we allow people to do that, right? In Cassandra and React, it doesn't really matter because you're looking up a single key. So tunable consistency levels doesn't matter. But for us, you're always going over a range of time. So you could be looking up 100,000 keys. So tunable consistency levels like quorum or all or whatever, it'll kill our data locality, but it'll give users that. The other thing we're talking about doing potentially is specifying a max stale age, right? So say you say a max stale age of a second. So when I send a query to a server, if it's lagged on replication by more than a second, it'll send a failure so that the coordinator node that received the query initially will ask another server for that data. The problem with time series data, this is another thing I said in the dotScale talk, is that you're always adding more data. So, what is consistent when you query a time series? If it's a time series that's sampling at, 1,000 hertz, what's consistent? Like, you basically have to stop the world and say, like, okay, this is consistent as of this exact microsecond, but 2 microseconds later, it's inconsistent.
Right. That's fair. So in a typical polyglot system, there's multiple databases working together to do different things. Are there any multi-database patterns that you see where people are doing specific things in conjunction with InfluxDB using other databases?
Specific patterns that we see?
Yeah, specific multi-database patterns.
I've seen a number of people pair Elasticsearch up with InfluxDB for answering other kinds of, like, Elasticsearch is better in many cases for some types of event data, and it's obviously better for log data because we don't do full text search, and that's not a focus of ours. So I've seen that almost. I mean, for cases where people are building, user analytics or analytics as part of an application they're building, they almost always have, what's called what I call like a canonical data store for their user data, which is generally a SQL database or MongoDB or Rethink. So I've seen that. And then another pairing that's frequent is actually using Hadoop and HDFS or S3 for long-term archival storage, right? So if you have a data pipeline where you're sending all your data through a queue, you have one consumer pull off that queue and write into Influx, and Influx is designed to only keep, say, the last 14 days worth of data in memory and hot. And then you have another consumer write compressed data into S3 or Hadoop, which is the archive of all the data, because it's cheaper to store. You can actually store all your data for all time there because you can actually just compress it a lot and it won't take up as much disk space.
So you've mentioned multiple use cases for InfluxDB for DevOps and data scientist people. Have you seen any new hybrid roles where DevOps and data science are merged into a single role, like a DevOps scientist?
I guess the closest thing I'd see to that are DevOps people who are working on systems for anomaly detection. Usually those people are actually, at this point, I don't think I've seen those people in large organizations. They're usually more at like companies that are building DevOps tools, like, like Datadog or New Relic or Vivid Cortex or one of those people.
Okay. What does InfluxDB's open source community look like?
How do you mean?
Are there any interesting community? Let's see, what's the best way to ask this? Are there any unique characteristics to InfluxDB's open source community?
I don't know that there are unique characteristics. I would say the lion's share of people of the open source community around Influx are people in DevOps roles or something related. But like I said, we see a lot of people in these other use cases as well. We do, I guess one key difference is there are a lot of people who like Go, who are interested in InfluxDB because it's written in Go. And I think, the rise in popularity of Go is something we've definitely benefited from because there are people who picked it up as a project or contributed to it specifically because it was written in Go. Whereas, a project like MongoDB is much harder for many developers to contribute to because it's written in C++.
The CEO of RethinkDB told me that they chose not to use Go because it was garbage collected. Does garbage collection provide a hindrance for you, or is it more of a feature?
Both. It's a feature because, so when we started the project, we had already had a system running in production that was our time series data store for a SaaS app, and it was built using LevelDB and Go. When we started InfluxDB as a project, we said, okay, either we can use the same tools we'd used before, and we know we'll get faster iteration, we'll get much farther along than we would get otherwise, or we can start fresh and write this thing in C or C++. And really, the only concern for me at that time was the garbage collection, right? Because I knew, like, as a database, you want to have really massive heaps, but massive heaps are, really horrible in GC languages. And I basically decided that, you know what, the iteration speed's more important, and there is prior art for building a database in a garbage collected language, right? Cassandra is a perfect example. So far there have been occasional hiccups as a result of it, right? A GC pause will kick in, and then the distributed system will think that servers aren't responding because they're actually paused on GC cycles. The nice thing about Go is they're continuously putting effort into improving the GC. And specifically the 1.5 release that is about to come out, the max, or the worst GC pause time is actually significantly reduced in that one. We haven't tested it yet, but we will be soon. And there are more GC improvements slated for 1.6.
What is InfluxDB, the company's business model?
So our business model has a number of different areas to it. One is managed hosting, which is obvious. Another one is support services and training. So we offer professional support at different levels for people who are running in production. And then, over the course of the coming year, we'll have closed source products that we'll release that are complementary to the open source offering that people can pay for. So it's not innovative in any sense in terms of like how you monetize an open source database company, right? Mongo and DataStax and Elastic all kind of do the same stuff.
Where is the company located?
Corporate headquarters is in San Francisco, but as a team, we're distributed. So we have people all over the place. Denver, Wisconsin, soon Boston, London, North Carolina, New York. I'm in New York maybe half the time, San Francisco a third or a half, and elsewhere in the world.
You hear some criticisms about distributed teams, especially from Y Combinator, from the Y Combinator startup podcast. I think Sam Altman has a lecture where he kind of disparages the idea of the distributed team. What has your experience with distributed teams been?
It's both good and bad. I agree that being in person is higher bandwidth, but the tools around being a distributed team keep getting better and better. And the one advantage that you have if you're building a distributed team is you're not limiting your talent by geography. There are talented programmers everywhere in the world. It's not like the Bay Area has a monopoly on talented programmers. And the fact is, we're able to hire people that are awesome that we wouldn't get if we were only hiring in the Bay Area. The thing is, if we're only hiring in the Bay Area, we're competing with all those other startups that are focused on, hiring all those engineers. Like, yes, the Bay Area has more engineers than, New York or Denver, Colorado. But the fact is, the competition for those engineers is 10 times worse. So that's nice. And the other thing we do is like we get together at least once every 6 months where we get everybody in the same place and we brainstorm and we do stuff. So far, I'd say it's a net win. And I understand, Sam Altman and all those people's like thinking is basically like, oh, you need your team together, so it's high bandwidth, high discussion, whatever. For us as an open source project, I think it's probably easier to be distributed because open source is generally, the development of the code is generally distributed in nature, right? You have contributions coming in from all over the world. So being distributed kind of keeps us honest in terms of using the tool chain that other people out there in the world, like the community, can see. because we have to use it to communicate with each other. So the community gets to benefit from that exhaust, right? They can see the issues on GitHub. They can see the pull requests.
Okay, well, Paul Dix, thanks for coming on Software Engineering Daily. It's been really nice talking to you.
Yeah, thanks a lot, Jeff.